All right, take a look at this equation. 14 divided by 2 plus 6 minus 14 divided by 2. We have all seen problems exactly like this blow up on social media and literally ruin friendships in the comment sections. Now, if you read this straight across from left to right, just like a normal English sentence, you'd calculate 14 divided by 2 is 7, plus 6 is 13, minus 14 is -1, divided by 2, well, that gives you -0.5. But if you actually follow mathematical hierarchy, the real answer is 6. That is a massive difference, and it perfectly exposes a fundamental gap in how we process numbers.
Welcome to This Explainer. Today, we're taking a deep dive into dismantling some of the most common, deeply flawed memory tricks taught in math. And we're going to replace them with a true structural understanding of how mathematics actually works. We're going to uncover exactly why so many people get completely stumped by those viral internet math problems, and more importantly, how we can fix that cognitive overload. We're moving away from arbitrary mnemonics and heading straight toward true fluency. So, let's dive right in.
Here is our roadmap for today's masterclass. We'll start by diagnosing the trouble with popular acronyms, explore the true four-tiered hierarchy of math, look at the linear misconception trap, and then equip you with visual modeling tools and real-world applications.
Let's kick things off with Section 1, the trouble with acronyms. Why do the very tools meant to help us remember actually end up sabotaging our understanding?
Notice the big red X over the staircase here. This highlights the inherent flaw in acronyms like bodmas, bidmas, or PEMDAS. We're taught to see these letters in a rigid vertical line, right? Brackets, indices, division, multiplication, addition, and then subtraction. Well, cognitive science research tells us that students naturally fall into what's known as the literal order assumption. Because A for addition comes right before S for subtraction in the acronym, the brain mistakenly treats that order as absolute law. It assumes you literally must always add before you subtract.
Let's actually see this trap in the wild. If we evaluate 6 minus 2 plus 3, a student who is clinging to that literal order assumption is going to force addition to jump the line. They'll calculate 2 plus 3 first, getting 5. Then they'll do 6 minus 5 to get an answer of 1. But as we know, addition and subtraction actually share equal priority. If we correctly evaluate this from left to right, 6 minus 2 is 4, plus 3 is 7. So the very mnemonic designed to guide them literally points them straight to the wrong answer.
Think about reading English. It's like driving straight down a highway. You just move forward, left to right. It's a completely linear process. But evaluating mathematical syntax, that is much more like exploring a branching tree. You have to scan the entire landscape first, identify the structural hierarchy, and only then resolve the calculation from the deepest branches outward. It's inherently recursive. Expecting someone to read an equation the exact same way they read a sentence is just setting them up for immediate cognitive failure.
Which brings us to Section 2, the four-tiered hierarchy. Let's uncover the actual structure of math.
You see, mathematical operations have an inherent hierarchy that comes from structural relationships, not just arbitrary rules someone made up. At the bottom, on Tier 4, we have additive operations, just your basic incrementing and decrementing. Move up to Tier 3 and we find multiplicative operations. Why? Well, because multiplication is simply compressed repeated addition. 4 times 3 is just 4 added to itself 3 times. Then Tier 2 is exponents, which is compressed multiplication. Because each higher tier is quite literally a more powerful compressed iteration of the tier below it, it logically must take precedence so we can unpack it correctly.
And sitting right up at the very top, in Tier 1, are grouping symbols. Now, here is a vital shift in perspective. Brackets and parentheses do not function as mathematical operations themselves. You can't do a bracket. Instead, think of them as a syntactic override. They're like a VIP pass, instructing the reader to skip the normal line, isolate that specific branch of the algebraic tree, and resolve it first before interacting with the rest of the equation.
So what happens when these linear rules actually fail us? Let's get into Section 3, the linear misconception trap.
Here's another classic trap for you. 12 divided by 4 multiplied by 3. If a student is strictly relying on PEMDAS, where M visually sits before D, they're highly likely to fall into that literal order assumption again and force the multiplication to happen first. 4 times 3 is 12. 12 divided by 12 yields 1. It's an entirely logical conclusion, but it's entirely incorrect because it's based on a completely flawed premise. To really shatter this misconception, we have to explicitly teach equal precedence.
Division and multiplication sit on the exact same structural tier. Because of that, we resolve them using a simple tiebreaker. We just read from left to right. 12 divided by 4 is 3, and 3 times 3 equals 9. The true answer is 9. This perfectly illustrates why teaching the actual structural tree is vastly superior and honestly just so much safer than handing out a simple linear acronym.
All right, so how do we actually fix this in the classroom? Section 4, Visual Modeling and Funneling, gives us some actionable pedagogical solutions.
Let's go back to our initial hook equation and look at something called the funneling method. Trying to do multi-step calculations in a single horizontal line heavily taxes a student's working memory. It's exhausting. Instead, we use funneling. We enforce a strict formatting policy where intermediate steps are written on separate lines directly beneath one another. In Step 1, we identify the Tier 3 divisions. Step 2, we evaluate them left to right, turning the expression into 7 plus 6 minus 7. Step 3, we process the Tier 4 addition. 7 plus 6 is 13. And finally, in Step 4, 13 minus 7 gives us 6. Notice how the calculation visually collapses downward? It literally looks like a funnel. This acts as a massive cognitive offload, freeing up brain space to focus on the structure rather than just struggling to hold floating numbers in their head.
And once students really grasp that visual funnel, we can push them into active learning with a bracket insertion challenge. Instead of just handing them an equation to solve, you flip the script entirely. You ask the student, where would you insert brackets to completely alter the structural integrity of this calculation?
You give them a target number, like 14. You hand them an equation that currently equals something completely different, and you say, place the brackets so that the final outcome is exactly 14. It's a brilliant puzzle. It forces the learner to stop passively solving and start actively analyzing how placing that syntactic override changes the entire flow of the math. They have to mentally map out multiple branches and hierarchies. It's an incredibly effective strategy for building deep structural comprehension.
Finally, in Section 5, Real-World Applications, we have to answer the ultimate question every student asks. Why does this actually matter outside of a math test?
We ground this theory by looking at something literally everyone cares about, a paycheck. Let's look at a very concrete scenario. An estate agent receives a weekly base wage of £750, plus a £100 bonus for every house they sell. This week, they absolutely crushed it and sold 2 houses. So the mathematical expression of their week is 750 plus 100 times 2. Now look at the massive difference operational precedence makes here. If you just do a linear left-to-right calculation, you add 750 and 100 to get 850. Multiply that by 2 and boom, you get £1,700. Now the agent would be thrilled, but the accounting department would be absolutely furious. The correct hierarchical calculation forces the multiplication to happen first, resolving that performance bonus to £200. Added to the base wage, you get the correct logical payout of £950. The order of operations isn't just arbitrary math torture, it's the strict rules of reality. Which leaves us with this final provocative thought to consider today. Are we truly equipping learners to understand the inherent, beautifully structured reality of mathematics? Or are we just teaching them to misread acronyms and cross their fingers for the best? By embracing the true structural hierarchy, we do so much more than just find the right answers. We actually learn to fluently read the language of the universe around us. Thanks for joining me on this explainer, and I'll catch you next time.